Hello everyone. So in the last class we were discussing about Ethereum, and we said in an Ethereum block you have a set of transactions just like in Bitcoin, but one of the additional things you have in the block is a hash of the state. So this is a hash value, it's like a unique ID for the entire state of the Ethereum virtual machine. So what we are supposed to do when we create a block is that you have these various transactions. Let's say you have T0, T1, T2 and so on, right? So all of these transactions have to be executed in order, and the state updated appropriately. And after updating the state, the new hash value has to be put in over here. Okay. So each transaction runs a piece of code which updates some state variables, right? And each transaction can either be said create smart contracts, or they can even run various functions in various smart contracts, right? So of course there are various rules for all of that. So maybe a particular smart contract might only authorize somebody with a particular private key, let's say, to run a particular function that might be there, right? So anyway, what happens is we execute each of these transactions one after the other, update the state. Okay, let's say that there are various state variables. And all of these are summarized in some hash value, which is what goes into the block, right? So let's think about it. Suppose there is a miner over here, and what is it going to do? So suppose we said that it has to run proof of work. So let's say this is the timeline, and suppose it is doing POW mining over here. So let's say this is the current blockchain that it has. Let's say this is the Genesis block. So this is so let's say this is the valid chain. So we're not considering any attack or anything over here. So let's say this is the current blockchain. So this miner, let's call it miner M2. Okay, this is the chain that it is observing. Now M2 has, let's say, already validated this entire blockchain. So it has its own potential block, just use this. So this is a block, a potential block which this particular miner M2 has created. So what it's done is in its transaction pool, it's taken some set of transactions, created a block like we've seen over here, right? It executed those transactions and it's updated the hash, right? But now it is doing POW. Right, so it's created its own potential block and it's doing POW. And let's say it gets another block, but from somebody else. So over here comes another block, okay, from let's say another miner M1. Okay, so this block shows up, okay, at this point in time. Okay. So what is M2 supposed to do over now, right? So we said that right now M2 is working on this block. It's trying to solve the puzzle for this block, and now another block comes competing with this one from somebody else, from some M1. Okay. So now what it has to do is that it has to validate M1's block, so what does this validation involve? It means that for M1's block, the transactions have to be executed in order, the hash updated, and then it has to be verified whether this hash value indeed corresponds to the one in the block. Okay. So validation means execute transactions, update the state, of EVM, and check if this state matches the hash in the block of M1. Right, so this is a new block which has come. M2 doesn't know whether this is a valid block or not, so it has to execute the transactions in M1, check if the state mentioned in M1 is correct, corresponding to that. Okay. And if that is valid, it has to create its own block. Okay, so now M2 is going to create another block, but now pointing to this one. So this one is discarded. Okay, assuming that this is valid. If this is invalid, of course, then it can retain this, right? Because this is not part of any chain if it's an invalid block. So M2 would continue mining on this one. But let's assume that it is valid. So it starts creating a new block. Okay. So what does it have to do to create this block? Well, it looks at its transaction pool. It has to get rid of the transactions which were there in this block from the transaction pool. And it puts in a new set of transactions which haven't been present in any other block in the blockchain. And it has to execute those transactions. It has to perform what I described over here. It has to execute the transactions, update the state, put the new state in the block, and then run POW on this block, right, and try to solve the puzzle. So this will also take some time. Okay. So now let's think for a moment. Let's call this. Let's say this is BK dash. Let's say this is BK, block BK, and this is BK plus 1 dash. So this POW mining is being done on BK dash. What should miner 2 do in this meantime, right? So over here, BK plus 1 dash is created. So what should this miner M2 do in between? So here it was mining on its own block. now it got another block, right? But it doesn't know if it's valid or not. So what would be the reasonable thing to do? Well, you continue mining on M2. That would make sense, right? Continue mining on this BK dash, right? Because you don't know if this one is valid. I mean, in theory, you could try to sort of create another block, but then the question is, what should be there in this block? Okay, that is one thing you have to decide on. Right? So you could, one option is you just keep mining on this because you're still validating what is, this is, if this block is correct or not. Suppose, let's say that this is one option. What do you do over here? Suppose it is valid, it takes some time to create your own block. What should you do now? Right? So the thing is, if you, an option 0 you can say would be that you just stop POW mining. You don't do any mining over here. And only after this BK plus 1 is created, you can mine on it. Okay, that's one thing to do. But if you don't mine, then the problem is, what if this block is not valid? What if M1's block was not valid? Then unnecessarily you wasted this time. Right? You could have just continued mining on this one, and maybe this was invalid, and then you created a block. Right? So might as well mine on this BK1, and when you have validated this particular block BK, which came from M1, you create your own block, right? So here, from here, it's clear that you're going to do POW mining on BK plus 1 dash. So here I'm sort of wasting some time if I just stop doing POW mining, but what should I do on? So I know that this one is valid, so there's no point mining on this one, right? But at the same time, I don't have my own block ready. I don't have BK plus 1 dash ready. So what should I do? Well, one option is that you create an empty block which is pointing to BK itself. So how does this help? Well, why do we do this? It seems a little bit weird, right? Because normally a block would have transactions, but here we are trying to mine on an empty block. Well, the reason is, let's just call this empty block, maybe I'm just drawing it this way to show it has few transactions. Let's just call this BK plus 1 double dash, and let's say that it's empty, has no transactions. So what does an empty block contain really? It doesn't have any transactions. Of course, it can have a coin base. So you don't have any transactions, so very quickly you can create an empty block. You just have to execute your coin-based transaction and update the state. So very quickly you can create an empty block and start POW. Okay. So this is a backup plan. So ideally you want BK plus 1 dash, which has a lot of transactions, to be ready so that you can get the transaction fees. But at the same time, you don't want to waste some time during the creation of the block, so you create this empty block immediately and you start mining on this. As soon as you've created BK plus 1 dash, you discard this empty block and you start mining on this block. Okay, so this is what M2 does. Okay, so option 0 would be that this entire time you don't do any mining, which is sort of a waste. Right? Option 1 is what I've shown. You continue mining on BK dash even when you have received this, because you're not sure if this is a valid block. As soon as you validated it, you mine on this one, which is an empty block, which you create very quickly. And once you have created this block, you start mining on it. Right? So it's a complicated procedure, but once you go into the details, I mean, we have to consider these things, right? Because we want to optimize this whole procedure. So what else could we have done here? Of course, I could have taken a risk, so that maybe I assume that this block is valid. I can at least check if the POW is correct. And if the POW is correct, maybe with high probability the miner has done a good job, who would mine a block and not have it valid, right? Maybe, but it's possible that some transaction wasn't executed correctly, but still, maybe I'll take a guess. I think first I'll validate only if the proof of work is correct, right? And then if that is correct, I guess that maybe the rest of the validation is going to go through, right? And what I could do is I could create this BK1 double dash directly on this, and I could start validating. I could start POW mining on that block here itself. Okay. So let me actually say this. Before we go to that, maybe I should talk a little bit about validation. So validation requires many things to be done. So one of the things is you have to validate the proof of work puzzle. And second, of course, is that you have to execute the transactions, right? So it's many different things have to be done. Okay. So let's see what is the option 2 for miner 2. And so this is POW on B dash K, right? And then you get BK. So this is validation of POW. So that is what I am showing here as 1. And I just draw this here a little larger. So I am expanding on what I showed over there. Validation of transactions. Okay. So what I could do is over here, of course, I just continue my POW on BK dash, and here I could do POW on BK double dash BK plus 1, the empty block. And then of course I create my own block. So during this entire time I do POW on this empty block, and now that I have my own block ready, I can do proof of work on BK plus 1 dash. Okay. So how is all of this possible? I mean, because when I'm creating my block, how is it possible to do POW at the same time? And we have to understand what hardware is used here. I mean, because you might think if I have just one processor, then I can only do creation, I cannot do POW at the same time, right? After all, POW is a computation itself. So we must understand how the proof of work blockchains work. So POW is usually done using ASICs. So ASICs are special purpose ICs which are designed specifically for doing proof of work. So the proof of work is done in the hardware so that it is done faster. Right? The more number of hashes you can compute, the higher the chances of your winning the puzzle, solving the puzzle first. So you want to do this as an ASIC. So of course when Bitcoin started and when Ethereum started, it was done on your regular CPUs or maybe GPUs. But since it's such a high stakes competition, people now want to do it in hardware. Right? So this is executed in an ASIC. Whereas the transaction validation, or I should say computation, is done on CPUs, right? So this is why you can have transaction validation and here to execute transactions. Okay, so by the way, this is both for BK. Okay, so you can have both of these running in parallel. Okay, so I'm assuming one CPU and one ASIC. The ASIC is doing POW and the CPU is doing execution of these various transactions, like the smart contracts and so on. Okay. So this is optimizing the resources, and here of course if you create a block suppose you solve the puzzle over here, I haven't shown that case over here, but suppose M2 was able to successfully create the appropriate POW on this empty block, it would have released that empty block into the net. Okay. So it might happen in Ethereum that if somebody solves the puzzle really fast before they even created their own block which has transactions, then you would have an empty block getting created. Right? So it's possible that POW blockchain might have empty blocks, even if everybody is honest, and I mean there's nobody trying to deliberately create empty blocks, but just it so happens that before they created their own block which had transactions, they successfully mined an empty block and they released it into the network. Okay. So this is how Ethereum works. Okay. So you want to optimize your chances of creating a block, so you want to continuously do POW. But at the same time, if it's possible that if we were using this option 1, here for example we are mining on the old block over here, even though we have received a competing block, just because we weren't sure of. Okay, so you want to finish this validation and creation pretty fast, because ideally you want to be mining on BK plus 1 dash. You want to get the transaction fees and you want to get your mining reward and so on, right? So ideally, if this particular step of the process where you're validating the received block and you're creating your own block, if that could be made 0, that would be best for you. Okay, because you don't want to end up mining an empty block because you don't get the transaction fees, and you don't want to end up mining on this, let's say BK plus 1, which could end up being a waste, right? Because already BK has been received by you, right? And if you have got this block and it's valid, then in the meantime, even if you successfully created POW on this one, it would probably not end up in the final chain, in the final longest chain, right? So this particular step of validating a received block and creating your own block should be kept as low as possible. Okay, so what does Ethereum do? So when you receive a block, I'll just say we validate the various steps of validation we complete, and then we create our own block, and then we do POW on newly created block. Okay, so this takes a lot of time, and currently what happens in Ethereum is that if I take this to be roughly 15 seconds, it's a very small amount of time, but that's what is set as interarrival time in and this is, let's say there's a new block, next block received. Okay, so this interarrival time is set to 15 seconds. So this is only about 1%, so this would be 150 milliseconds roughly. Okay, so the computation in blocks is kept so small that it gets done in hardly 150 milliseconds. That's what our own experiment show and what we've published in our papers, right? So very quickly you compute what is there in a block. So what is the drawback of this? Well, if you had like a dedicated, let's say PC, which was continuously executing transactions, that would have been able to process 100 times what Ethereum is doing right now. Okay, because currently over here your CPU is idle, so only 1% of the time the CPU is sort of being active and it is executing transactions. So even if Ethereum is, let's say, $500 billion indus whatever worth, I mean the value of Ethereum maybe of just Ether is 500 billion, let's say, right? It may go up or come down. It's doing very little computation. The smart contracts being executed use up only 1% of the computation time of the CPU, right? So the Ethereum computation in fact is equivalent to, let's say, what the small chip on your credit card could do. It's not doing much at all. So you might say, why should it be 1%? Why not make it 10% or 20%? What could go wrong over there? So if we look at this figure, we'll get a better idea. So let's look at this particular situation. Okay, so of course there are different strategies to be followed. We looked at these two options. I said this is option 1. So what happens over here? So if I'm saying that I stretch this out, instead of it being 150 milliseconds, which is hardly any time, what if I make it 1.5 seconds or 5 seconds or something like that? What's going to happen over there, right? So then let's say that I'm mining on this one, which was my original block. Okay, so this is bk minus 1. Okay, this was the k minus 1 block in the chain. Suppose I got a potential bk, and using this particular strategy I am mining on this old block of my own old block, okay, which was pointing over here, because I haven't yet validated this. I don't know if it's correct or not, right? So suppose this time is long, then what happens? I'm spending a lot of time mining on this, and what if this block is valid? This block is valid, then I should be trying to create something on this block, because this block has already been broadcast into the network. And even if I successfully create a block in this time, I would have wasted a lot of time. I would have wasted my POW energy on this block, which anyway nobody is going to accept in their blockchain, right? Because this one, people will eventually validate this, and since they got this one before my own block, they will take this block rather than my own. So this is time wasted, okay? Even if I am successful over here, it would be a waste, right? But another option is that I don't mine on this block, okay? So what I can do is I can just create, let's say, an empty block, and continuously I mine only on this, right? So it's sort of like I've shown partly that option in option 2, but even here, okay, so let's say that I'm doing option 2. So what could happen? So suppose I'm trying to create, I don't want to mine on this one, okay, so I'm mining on BK11 dash, and this is a long period of time. Let's say it takes me 5 seconds, right? And at the end of this time, I realize that the block is invalid. So suppose BK is invalid, but I find out all the way towards the end of this validation time, then so much of time was wasted on mining BK plus 1 double dash, which is this empty block, and I was unnecessarily creating this empty block on an invalid block, and so this was a waste of time. Okay, so this what I've just described is called the verifier's dilemma. Okay, so I can effectively I can try to create a block on this one, either an empty block or even a block with transactions, it doesn't matter. But while I'm validating this, I'm confused. What should I do? Should I mine on this block, which would be a bad decision to make if this is valid? And mining a block on this one is also a problem in case this is invalid. Okay. So what should I do? That is the dilemma that this verifier M2 is in, and it's called the verifier's dilemma. So suppose a block validation time is large. Let's say it's suppose 5 seconds. Okay, so I mean large relative to the interarrival time between blocks. Then what do I do? So let's say that I receive this BK over here, and now I'm going to validate BK. It involves looking at the POW and validating the transactions. So mining on BK dash is a waste if BK is valid. Okay, so during this time, okay, and this is one strategy, and another strategy is mining on, let's say, BK plus 1 double dash. This is a waste if BK is invalid. Okay. So this is the dilemma what to do, and it's a problem for us because we are not saying that miner M2 is malicious or anything. It's an honest miner, but it's in this dilemma because it doesn't know whether it has got a block from an honest miner or not, right? So what should it do? I mean, if it follows this strategy, it could be a waste of time. If it follows this strategy, again it is a waste of time. It could be a waste of time, right? Depending on whether the block is valid or invalid. So if you were a miner, what would you do if you had these two options? Should you follow the rules and say that I will only mine on a block only after validating it, in which case you follow this one? Or would you follow this one? You say that even if before validating the block, I will try to create a new block on it, even an empty block, and then mine on it, right? So the problem with the second option is that you could have somebody generating an empty block, even if the POW here is valid, but it could be generated on an invalid block, BK. Okay, so that would be a waste, right? And so you never know what to do over here, right? So what Ethereum does is that it keeps the gas limit low on a block so that the block gets validated in about 1% of the time. Okay, so that the verifier's dilemma is reduced. Okay, so which of these you follow is not going to impact so much the blockchain if this time for validation is very small, right? But if it becomes larger, if you increase the gas limit so that instead of 150 milliseconds for validating a block, it takes, let's say, 3 seconds or 5 seconds, then the verifier's dilemma is non-trivial. Okay, that a miner has to choose between one of these, both which could be problematic, right? Because it takes a long time to validate a block, right? So we have done some analysis in some of our papers too on this, and of course other people too. A group in Singapore was the first one to actually point out what this verifier's dilemma is and so on. Okay. So this is an issue, and it has kept the gas limit very low in Ethereum and the computation very low. Okay. So the question is, what should we do? How can this be remedied? Okay. And I'll just give you a brief overview of two of our papers, and the person who has been leading this effort was one of my former BTech students, Saurabh Das. So the first piece of work he did was we called Yoda, and of course it's not an acronym for anything, it's just a nice name. So this he did actually as part of his BTP project when he was with me when I was at IIT Delhi. Okay, and it appeared in one of the top conferences, the NDSS conferences, right? So very good work. All the reviewers said that this is very new, right? They had never seen something like the solution he had proposed. And then of course he had 1 year gap between his PhD and his BTech, so he joined me here at IIT Bombay, and along with Nitin and other students, we came up with another solution called Tuxedo. Okay, so I'll talk about both of them in our lectures, in the subsequent lectures. But of course the flavor is quite different. So what Yoda does is it's an offline solution, and this one is online. So of course these are terms that we coined, but they mean slightly different from what we mean by offline and online for the internet. So by offline I mean that the computation is not done by the miners. Okay, so what I'm saying is that if we increase the gas limit, a lot of the computation is not done by the miners. So this was a counterintuitive idea. So what we are saying is that we actually keep the validation time for the miners very small, but we offload the computation to somebody else. Okay, so it's a counterintuitive idea, and we'll see how it works. But there are some drawbacks to this, okay, and with relation to smart contracts interacting with each other and so on. Okay. So Tuxedo solves that. So here all the computation is done by miners, which is what Ethereum does. But the trick is that we delay the validation by some amount. Okay, so what Ethereum is doing is that as soon as you get a block, you validate it, right, and then you create your own block, and then you start mining on the new block, right? But we are saying that we are willing to delay this validation. Even though we have received VK over here, we can do this validation sometime in the future, and we can immediately create a block and start doing POW. Okay, so both of these solutions are somewhat counterintuitive, and we'll see, I mean, how to get everything working and what sort of analysis we did and so, right? So that we'll start off with Yoda in the next class, right? But the idea is that we want to give the computation to somebody else, some third party, let's say, and then the question is, how do you know that they're doing the computation correctly or not? Okay, so that's really where the solution comes in, which we proposed in our paper.